Hello, everyone, and thank you for attending my talk. I'm Johnathan Avery. I'm a graduate student at Indiana University in the mostly cloudy town of Bloomington, Indiana. This work was done in collaboration with Drs. Rob Goldstone and Mike Jones, who are faculty here at IU. This work is blandly titled Reconstructing Maps from Text. The theme of this project was to see how we could take the statistical structure that is embedded in maps, encode it in language, and then recover the map by using models of distributional semantics. We test numerous distributional semantic models under multiple conditions in order to pin down why these models are able to perform the recovery of spatial information from linguistic descriptions. So here's the general flow that this talk will take. I'll start by giving you some background on distributional semantic models and why we would even think of applying them to the task of reconstructing maps. Next, I'll discuss the general methodology we'll apply between these two studies I present, and then I'll present the findings of those two studies. Finally, I'll conclude with a brief but more concrete restatement of this last paragraph. So let's begin with some background on distributional semantic models. Distributional semantic models operationalize word meaning by tracking statistical regularities of words in a text corpus. Commonly, these models construe the regularities as points in high-dimensional vector space. By applying rules appropriated from linear algebra, the similarity between words can be calculated as the proximity between words in this high-dimensional space. Now, while distributional semantic models have shown remarkable success at accounting for a broad range of semantic phenomena from relatively simple mechanisms, a major criticism of these models is that the representations are amodal and are grounded in neither perception nor action. As a counterpoint to this criticism, however, two previous applications of distributional semantic models toward the task of map reconstruction demonstrate that spatial distributions can be encoded in language, and that semantic processes posited by DSMs are able to elicit these spatial distributions independent of perceptual grounding. Specifically, Louwerse and Zwaan reproduced maps of the United States by applying latent semantic analysis to various large news corpora. Later, Louwerse and Benesh followed up with a study demonstrating that even the relatively small corpus of the Lord of the Rings trilogy, latent semantic analysis was able to adequately reproduce a map of Middle-earth. So contrary to the assumption that spatial representations are fundamentally perceptual and are necessarily grounded in sensory modalities, the reproduction of maps demonstrates that spatial distributions can be encoded in language and that semantic processes are able to elicit these spatial distributions independent of perceptual grounding. But while it's cool and fascinating that Louwerse and his colleagues were able to recreate these maps, the source of the success remains murky. Specifically, it's unclear what the statistical properties of the corpus are that enable spatial distributions to be reconstructed from the text. Is it the case that these models work because they create a higher order abstract representations of the city words? Or could it be that the success is mediated by frequency? Cities that are near one another may be discussed in the same contexts or the same sorts of contexts more frequently, while contexts that relate distant cities occur infrequently. And so the specific goal of this project is to examine the hypothesis that is actually this frequency of co-occurrence that's driving the success of these model demonstrations. So here in this section, I'll present the general methods that were consistent between the two studies. In this section, I'll, just go through each of them briefly, and then I'll give you more depth subsequently. So first, we randomly generate a set of maps, and then for each map, we generate a corpora that described the layout of the cities on the map. Then we train semantic models using these text corpora, then using the cosine similarity matrices from these semantic models, we generated two-dimensional projections of the maps, and finally evaluated each reconstruction. Okay, so that was a lot of steps without very much detail, so allow me to break down the steps with more information. We started by randomly generating 3 different maps. We structured the 3 maps differently in order to vary the level of complexity and visual interpretability. Each map was composed of 20 cities labeled A through T. Here I show the 3 maps we generated. On the left is a random distribution. The center is a clustered to clustered distribution of cities. And then the map on the right is just a shape. So for each of these maps, we generated statements that related 2 cities to one another. The statements took the form of city label, relationship label, and then city label. We used 2 different relationship sets, near to versus far from, and then north, south, east, west of. So for each relationship set, we generated a statement relating each combination of cities. So for each map, we'd have a set of statements sounding like A is near B, C is far from D, and then another set of statements sounding like A is north of B, C is west of D. And then once we had each of these each set of statements for each relationship set for each map, we generated the corpora. Specifically, for a given statement set, we sampled statements from the set in order to generate 2 corpora. One where each statement has an equal probability of ending up in the final corpus, and then one where the probability of the statement occurring in the final corpus is inversely proportional to the distance between 2 cities in the corpus. Each final corpus was a total of 10,000 statements. So the combination of the type of map, the relationship set, and the sampling procedure represents a variety of conditions meant to explore the capacities of model performance. However, the key manipulation for this work was the frequency of sampling. So next, we trained a variety of semantic architectures on each of the corpora. After training, we measured the cosine similarities between all the cities, then translated them into distances using Shepard's law of generalization. We then used multidimensional scaling to produce a 2-dimensional projection of each proximity matrix. And finally, at long last, we have the map reconstruction for the model, which we could evaluate against the original using bidimensional regression. So bidimensional regression is a tool that was invented by geographers explicitly for the use of comparing maps. It yields numerous coefficients, but the one of interest for this work is the R coefficient, which describes the degree to which 2 points or 2 plots align. So here we are now to the point where I can show you what we found with regard to standard DSMs. Specifically, this first study looks at whether standard DSMs can reproduce maps independent of sampling condition. So in our first study, we used LSA, positive pointwise mutual information, continuous bag of words, and glove. But in the interest of time, I'll refer you to our paper or to the original papers for their various operations. So for each of these architectures, we trained a different model for each corpus in our set of corpora. Now, this next slide, I present a visual demonstration of the capacity of glove to reproduce the maps in the uniform sampling condition. We chose glove here as an example because it was a high performer in this condition. Here we used the north, south, east, west to describe the relations between each of the cities. The top row are the original maps, the bottom row are the glove reproductions. I've listed the R coefficients in red with their statistical significance for each of the reproductions. Notice that glove was only able to produce a statistically significant reproduction of the map in the clustered condition. This next slide mirrors the previous, except now I'm showing the distance-based sampling condition. Not only do the visuals provide a compelling demonstration of the capacity of glove to reproduce the maps in this condition, each reproduction is also statistically significant. Here I present a table with the R coefficients and the significance of map reconstructions for each model and each map distribution as listed in the first and second columns. The third column shows the model's performance for a map in the uniform sampling condition, and the final column shows the performance in the distance-based sampling condition. Note that I'm only showing the results for the north, south, east, west relationships for conciseness. You can refer to our paper for the complete data. Note that hardly any map reconstructions in the third column are significant, as denoted by the asterisks, while all of the reconstructions in the fourth column are. The key trend of note is that standard DSMs are not able to consistently reproduce maps independent of sampling. Now in study 2, we present a model based on Johnathan and colleagues' instance theory of semantics. And then we demonstrate that the model is able to reproduce the maps independent of sampling. Briefly, ITS is a trace-based model. Each learning instance is stored as a unique trace in memory. At the time of retrieval, a probe differentially activates each learning instance, which are then summed into the final output representation, which is referred to as the echo. Only the traces in memory that highly resemble the probe contribute strongly to the echo. Now we modify the model in 2 ways. First, we modify the echo. Note that the echo is composed of traces that resemble the probe, so naturally the echo contains the original elements of the probe itself. We amplify the context sensitivity of the model by subtracting out the probe. This yields a composite of the contexts in which the probe occurs. Second, we modified the means by which similarities are evaluated. Rather than taking the direct cosine between words, which would render the same result as the standard DSMs, we instead define the similarity of between the 2 words as the sum of similarities between the words in terms of tertiary words in the corpus. So allow me a brief illustration to clarify. Normally in a standard DSM, word similarities are garnered via a direct cosine similarity between 2 words. Instead, what we do here is we find the context of the 2 words with some tertiary word. And then we find the similarity between those 2 contexts. That is, we find the relationship between the 2 words relative to some other word. We do this for every word in the corpus, which isn't hard with these corpora since the vocabulary set is small, and then sum all of them together. This retrieval mechanism implements the idea that abstraction occurs at the point of retrieval and that relationships between words occur on the fly, rather than being a static cosine similarity measurement. So how does this model perform? On this slide, I present a visual demonstration of the capacity of our modified ITS to reproduce the maps in the uniform sampling condition. Again, we used the north, south, east, west to describe the relationships between each sentence or between each city. Simply, ITS was able to garner a statistically significant reconstruction of each map. Now here on this next slide, I show the overall performance of our model. The first column denotes the relationship set used, the second denotes which map was used, and the third and the fourth columns hold the values for each sampling condition. A quick glance at the statistical significance of each reconstruction reveals that the ITS model is able to reproduce the maps independent of sampling conditions. So, in conclusion, demonstrations by Louwerse and his colleagues show that spatial distributions can be elicited from text. Given that amodal distributional semantic models are not grounded in any perceptual input, it is surprising that they can reproduce spatial distributions whatsoever. So here we bring sampling frequency under experimental control to demonstrate that frequency of co-occurrence is providing the statistical redundancy that enables standard DSMs to reproduce spatial distributions. Our first study demonstrates that standard DSMs can't reproduce maps independent of sampling frequency. Our second study demonstrates that we can reproduce maps independent of sampling by using an instance-based model of semantic memory that constructs relationships between words on the fly. Let's see, so the code for this work is available at my GitHub, and you can feel free to contact me at the email address provided here. I'd like to thank my collaborators Rob Goldstone and Mike Jones for their contribution to this work, and thank you all very much for your time.